In this chapter, the different states of matter will be discussed. Let's start with a model for gases. The word kinetic refers to motion. Kinetic theory explains that all matter is made of particles in constant motion. For gases, the particles are considered small, hard spheres. The motion of gas particles is rapid, constant, and random. All collisions between gas particles are perfectly elastic, which means that there is no loss of kinetic energy. Gas pressure is defined as a force per unit area exerted by a gas on an object. The SI unit for pressure is Pascal. Vacuum is empty space without particles and consequently there is no pressure. Atmospheric pressure is the result from collisions of atoms and molecules in air with objects. When a substance is heated, its particles absorb energy. Part of this energy speeds up the particles and results in an increase of the kinetic energy, which leads to an increase in temperature. The average kinetic energy is proportional to the temperature. The particles in any collection of atoms or molecules at a given temperature have a wide range of kinetic energies. Some particles have a low kinetic energy. Most particles have a kinetic energy close to the average value for the collection, and some particles have a high kinetic energy. At any given temperature, the particles of all substances, solid, liquid, or gas, have the same average kinetic energy. The average value is proportional to the substance temperature in Kelvin. An increase in the average kinetic energy of the particles causes the temperature of a substance to rise. Particles in liquids have kinetic energy, which allows the particles to flow. The ability of gases and liquids to flow makes them take the shape of their containers. The particles in a liquid are attracted to each other, while particles in a gas are not. That's why liquids have a definite volume. The volume remains constant. Consequently, liquids are denser than gases. A puddle will eventually dry up. The change of a liquid to a gas is called vaporization. When this conversion happens at the surface of a liquid that is not boiling, the process is called evaporation. The difference between evaporation and boiling is shown in this table. Evaporation occurs at all temperatures, but only the particles with enough kinetic energy which are at the liquid's surface will be able to escape. As evaporation takes place, the liquid's temperature decreases, so evaporation is a cooling process. Boiling occurs for all particles in the liquid at the boiling point. During the process of boiling, the temperature remains constant. When a partially filled container of liquid is sealed, some of the particles at the liquid's surface will vaporize. These particles collide with the walls of the container, producing pressure. Over time, more particles will vaporize, but some particles will return to the liquid phase. This is called condensation. Eventually, the number of particles condensing will be equal to the number of particles vaporizing, and the pressure will remain constant. The vapor pressure of a liquid can be measured with a U-tube manometer filled with mercury. When there is only air in the container, the pressure is the same at both sides of the U-tube. When a liquid is added to the container, the pressure in the container increases. The vapor pressure of the liquid pushes the mercury down on the container side of the U-tube. You can determine the vapor pressure in millimeters of mercury by measuring the difference between the two levels in the U-tube. As shown here, the vapor pressure increases as the temperature increases. In this graph, the vapor pressure versus temperature is shown for different liquids. We notice that as the temperature increases, the vapor pressure increases. The curve in red is for water. At 100 degrees Celsius, the vapor pressure of water is equal to 101.3 kilopascal, which is the atmospheric pressure at sea level. Heating a liquid allows a greater number of particles at the liquid's surface to escape, and the average kinetic energy of the particles in the liquid increases. As the temperature increases, the vapor pressure increases. When all the particles in the liquid have enough energy to vaporize, the liquid boils. The boiling point decreases at higher altitude, because the external pressure is lower. The temperature of the boiling liquid never rises above its boiling point. If you heat the liquid more, the liquid only boils faster. The normal boiling point is the boiling point of a liquid at a pressure of 101.3 kPa. In most solids, the particles are packed tightly together, so solids are dense. Particles in solids tend to vibrate about fixed points, so solids do not flow. When you heat a solid, the organization of the particles within the solid breaks down, and at a certain temperature the solid melts. The melting point is the temperature at which a solid changes into a liquid. The freezing point is the temperature at which a liquid changes into a solid. Melting and freezing point occur at the same temperature. Most solids are crystalline. In a crystal, the particles are arranged in an orderly way. The smallest group of particles within a crystal, that retains the geometric shape of the crystal, is called unit cell. A crystal has sides or faces which come together at specific angles. Some solid substances can exist in more than one molecular form. These are called allotropes. Allotropes are made of atoms of the same element. Examples are phosphorus, sulfur, and carbon. Below, some allotropes of carbon are shown, which are diamond, fullerene, and graphite. Some solids are amorphous. This is a solid with randomly arranged atoms, example, glass. Solids with vapor pressure above atmospheric pressure may change from the solid state directly to the gaseous state without passing through the liquid state. This is called sublimation. The process of deposition is when gaseous particles can change directly to solid particles. Example, when iodine crystals are heated, they undergo sublimation. The crystals go directly from the solid to the gaseous state. When the iodine vapor cools, for example when the gas particles come in contact with a cool surface, it goes directly from the gaseous to the solid state. Solid air fresheners contain a variety of substances that sublime at room temperature. Water exists in solid, liquid, and gas forms. Each phase is reversible. Matter changes between phases according to temperature and pressure. A phase diagram gives the conditions of temperature and pressure at which a substance exists as solid, liquid, or gas. The triple point describes the only set of conditions at which all three phases can exist in equilibrium with one another. Looking at the phase diagram, you can determine what happens if you melt ice of boil water at pressure less than 101.3 kPa. A decrease in pressure lowers the boiling point and raises the melting point. The last part of this video shows vapor pressure in more detail.
Look at this little experiment here. It's a closed chamber, and let's pretend that at the beginning we have only liquid water present. There's no gaseous water vapor present initially. So that means our vapor pressure here, as indicated on the little gauge, is 0. That's our initial state. But as we go on, we have water beginning to evaporate into water vapor, and we start to get a collection of water vapor molecules in the air over the water. The evaporation is occurring at a rate that is set primarily by the temperature of the water. So evaporation and temperature are tied together. As we get those water vapor molecules over the water, some begin to condense back into liquid water. And the rate of that condensation depends on the amount of water vapor molecules that are present. So as time goes on and we get more and more water vapor present over the water and our vapor pressure increases, our condensation rate continues to increase until it equals the evaporation rate. And when that happens, the vapor pressure is equal to the equilibrium vapor pressure. The condensation rate is equal to the evaporation rate. That's the state of equilibrium when all those things are equal.